Let us look at how microscope magnifies. The angle at our eye decides the appearance of the size. So if the object is say over here, it is going to make some angle. If the object comes closer, the angle increases. If the object comes further closer, the angle increases further, and if it is very close, the angle can be very large. In general, angle subtended is inversely proportional to the distance of the eye. Now for a lens, the formula given is the relation between image and object is 1 by v equal to 1 by u plus 1 by f, when especially we are using Cartesian convention, that is the distances on the left hand side are negative and distances on the right hand side are positive. Now here is a convex lens, there is a focus over here, and this is the principal axis. If the object is placed at a large distance, using guiding rays we can find out where the image will form. So you can see that the image should form at this particular point, okay, and it will be a small image. Now if the object comes closer, we can have one guiding ray the same, and the other guiding ray passing through the center of the lens can tell us that the image should form at this particular point. Similarly, if the object comes even further, the image formation is going to be at greater distance, okay, and the size of the image will also go on increasing. Now note that angle of the object at the lens is equal to angle of image at the lens. So there is no angular magnification. It is just that because the object is forming at the image is forming at greater and greater distance for the same angle, the image size goes on increasing. Now for a human eye, it is slightly different thing, because there the screen is at a fixed distance, so the retina is fixed, and here what happens is the eye adjusts the focal length. So say object is over here and this is the lens, and for this particular lens let's suppose the focus is at this point. Then what will happen is we can draw the guiding rays, and the ray parallel to principal axis will pass through focus, and the image will form on the retina. So the focus is adjusted so that the image forms on retina. If the objects come closer, what will happen is the focus shifts, so focus becomes smaller, okay, or the focal length becomes smaller, and the lens effectively bulges, and again it is adjusted in such a way that the image again forms on the same screen on the retina. If an object comes even closer, okay, the focal length will further shift here, and what you observe here is again the image is forming on the same screen, but now as the angle also goes on increasing, the object is coming closer, okay, and the image is also forming at a greater distance from the focus. The size of the image also goes on increasing, and we see that the object has effectively become larger and larger. So as you take the object close by, effectively what happens is it is subtending large angle, and then we see the object as large object. Now we can't keep doing this for whatever distance. Objects come closer, the focal length is reducing, but focal length can't reduce beyond certain limit for an eye. So what we observe over here is this is the structure of the eye. When the rays are coming from very long distance, effectively the rays are coming parallel, and they will get focused on the retina when the eye is relaxed effectively, and the focal length is large. Now when the object comes close by, the lens of the eye needs to bulge, and the focal length reduces, and effectively it reduces such that again the image is forming on the same screen, same retina. So there is a limit up to which the eye lens can reduce the focal length. A normal human eye cannot see object closer than about 25 centimeter or about 10 inches. So you may be more precise, about 25.4, but this is an approximate number. This is called distance of distinct vision. Now if you consider a simple microscope, which is single lens, what we are doing is, in simple microscope we employ a single converging lens or a convex lens. This lens converges the rays into eyes so that the image from a closer than 25 centimeter object can form on retina. So what is happening is you can take the object closer than 25 centimeter. Naturally it is going to subtend large angle at the eye, but then it needs to be converged on the retina, and therefore you need additional converging power, and that additional converging power is given by the converging lens. Now it just helps to reduce the effective focal length of the eye's lens. So how do we calculate magnification by simple microscope? Remember that angle is not changing. Okay, so for small object, normally one would keep the object as close as possible to see it bigger. The distance for normal eye is 25 centimeter. That is, at about 25 centimeter, if you keep object, okay, that is the closest distance at which you can keep an object and still see good image. Okay, this is for normal human eye. Of course, one may need to correct the eye depending on whether one has myopia or hypermetropia. To magnify the object 2.5 times, the object should be kept at 10 centimeter distance. Okay, then angle will be 2.5 times larger, and therefore we will see that as 2.5 times bigger. However, we can't see object kept at 10 centimeter without any extra help. So we may have to employ a convex lens with a focal length of about 10 centimeter. So what happens is, when the object is kept at the focus of the lens and the lens is almost touching your eye, the emerging rays from the lens are going to be parallel, and our eyes will be able to see it in a relaxed position, as if the rays are coming from very distant object, and the eye will be in most relaxed position. So if I use focal length of 10 centimeter, then I can keep object as close as 10 centimeter, and I will see that as a big object. So this gives typically magnification of 25 centimeter divided by 10 centimeter, that is 2.5x. If I keep the object at 5 centimeter, then I'll need a focal length of 5 centimeter. Okay, I'll need a lens with a focal length of 5 centimeter, and in that case the magnification is going to be 25 divided by 5, that will be 5x magnification. Now magnification, we can use similarly different kind of smaller and smaller focal lengths, and we can have larger and larger magnification. So general formula for simple microscope magnification will be 25 centimeter divided by f, which is focal length of the lens measured in centimeter. Now if we use compound microscope, we use lens system. So in compound microscope, you have an objective lens, and let's draw up a principal axis over here. Now this objective lens will have certain focus, okay, and generally you'll keep object slightly beyond the focus. So the object is kept slightly beyond the focus. Now it is going to form an image. So using ray diagram, using guiding rays, we can draw a ray diagram. So there will be one ray passing through the center of the lens, another ray passing parallel to principal axis. After passing through the lens, it will go through the second focus, and it will form effectively a large real image. Okay, it is going to be large real inverted image. Now we need second lens such that its focal length is at this position. So what we do is, we keep the second lens, okay, called eyepiece, at such a position that its focus matches with the position where this image is formed. So the focal length of this eyepiece is here, and this is the focal plane. Now see what happens. This is the point where it is a point on the focal plane. So after passing through the lens, the rays are going to go parallel. But where will they go? In which direction they go? For that we will have to use some kind of guiding ray. So what we do is, from this focal plane we pass a guiding ray through the center of the lens, and that will give us an idea that the ray will go something like this. Okay, and so all the rays which will be coming from this particular point, after passing through the lens, will go parallel to this particular line, and therefore we can draw the rays which are actually coming from this particular object at this tip, okay, will be going like something like this. The ray which is coming from the other point of the object along the principal axis will go straight, and what we observe now is the two different ends of this particular object are going to sustain this large angle, and that's why we are going to see this as a large image. Okay, with our eyes we are going to see this as a large image. Now we can calculate what is going to be the focal length, okay, for such kind of combinations. So what is generally observed is, in a standard compound microscope, the distance between the second focus of objective and the first focus of eyepiece is kept fixed. That is called tube length, and it is about 160 mm. So this tube length is generally fixed, and the distance effectively therefore between the objective and the eyepiece is also fixed. When you want to focus the object, generally it is the entire assembly that you are moving, so that the slide or any object which is kept beyond the objective is well focused. Now let us see what is the formula for magnification. So magnification by objective lens is given by V by U. This is for a single lens formula, and we know the relation 1 by V is 1 by U plus 1 by focal length of objective, and then you can multiply by V, and effectively you get 1 equal to V by U plus V by F of objective. Okay, and you can rearrange the term that V by U is magnification by objective, and that can be written therefore as 1 minus V by F of objective. In magnitude, then it is going to be F of objective minus V divided by F of objective, and we have already seen here that this distance, okay, the image distance minus F of objective is the tube length. So considering this, what we do is we can write that F of objective minus V in magnitude is the tube length. Okay, and we can write the formula that magnification by objective is approximately minus L upon F of objective, because this V minus F of objective is L, and therefore we are writing this negative sign over here. Now we need to find out what is the magnification by eyepiece. So eyepiece here is acting as a simple microscope. Okay, we are keeping the image which is formed by objective at the focus of simple microscope, at the focus of the eyepiece. Now magnification of eyepiece we have already seen is distance of distinct vision upon the focal length of eyepiece, and therefore the total magnification will be magnification by objective into magnification by eyepiece, and this magnifying power then we can be given as minus 160 by focal length of objective multiplied by 250 divided by focal length of eyepiece. These numbers are given in millimeters, and therefore the focal lengths of objective and eyepiece should also be given in terms of millimeters. Negative sign is only going to indicate that the image is going to be inverted image. So if objective as 4 mm is used, then magnification by objective is going to be minus 40, because it is going to be minus 160 divided by 4 mm, 160 mm divided by 4 mm, and it will be marked as 40x eyepiece. With 10x eyepiece, okay, 40x objective here, and with 10x eyepiece we are going to have magnifying power as 400x, because this is going to be 40x and this is going to be 10x. So that will be effectively 400x magnification. Thank you.